Have you ever wondered if space could bend so much that reality itself breaks? Could the universe twist and fold in ways we can't even imagine? If space isn't as fixed as we think, what does that mean for our understanding of reality? These are the questions that push the boundaries of science and philosophy. What happens if the fabric of space itself bends too far? Could it reshape everything we know, or even tear reality apart? Join me as we explore these mind-bending ideas and see what happens when space and reality collide. The fragile edges of the universe. When we think about the universe, it's easy to imagine it as something vast and endless, with no boundaries or edges. But one of the most intriguing questions in cosmology is whether the universe has a specific shape, and what that shape means for its future. This is where the concept of spatial curvature comes into play. In simple terms, spatial curvature refers to how space itself bends or curves, depending on the amount of mass and energy present in the universe. Now, the idea of curved space might sound a bit abstract, but it's actually a central part of how we understand gravity and the large-scale structure of the universe. According to Einstein's general theory of relativity, massive objects like stars and galaxies bend the fabric of space around them, causing the effect we recognize as gravity. It's like placing a heavy ball on a trampoline. The surface bends around the ball, and anything else on the trampoline gets pulled toward it. This bending or curvature also happens on a much larger scale, across the entire universe. Scientists have developed three main models to describe how this curvature might work on a universal scale: flat, open, and closed. These models aren't just about geometry. They tell us a lot about how the universe might evolve and what its ultimate fate could be. In a flat universe, space is essentially uncurved. Think of it like a perfectly flat sheet of paper. If you draw two straight parallel lines on that sheet, they'll stay parallel forever, no matter how far you extend them. This means that, on the largest scales, space is evenly distributed and doesn't bend in any particular direction. A flat universe would continue to expand indefinitely, but the rate of that expansion would slow down over time as the force of gravity tries to pull everything back together. However, gravity wouldn't be strong enough to stop the expansion completely. It would just slow things down, possibly leading to a distant future where everything spreads out so much that galaxies become isolated, stars burn out, and the universe becomes a cold, dark place. This is sometimes referred to as the Big Freeze. An open universe is different. In this model, space is curved in such a way that it resembles a saddle or a hyperbola. If you were to draw those same two parallel lines in an open universe, they would eventually diverge. They would move farther and farther apart as you extended them. An open universe would also keep expanding forever, but unlike the flat model, the expansion wouldn't slow down. Instead, it would accelerate. In this scenario, the universe expands faster and faster, with galaxies moving away from each other at increasing speeds. Some scientists have theorized that in the far future, this could lead to a big rip, where the expansion becomes so extreme that even the fabric of space itself is torn apart. Then there's the closed universe model. In this case, space is curved like the surface of a sphere. Imagine drawing those two parallel lines on a globe. Eventually, they'll meet. A closed universe suggests that space is finite but without boundaries, much like how you can travel around the Earth without ever encountering an edge. The key difference here is that, in a closed universe, the expansion of the universe would eventually stop, and gravity would cause everything to collapse back in on itself. This would result in what's known as the Big Crunch, where the universe essentially rewinds, shrinking down to a hot, dense state, similar to how it began with the Big Bang. Each of these models, flat, open, and closed, tells us something different about the long-term future of the universe. But how do we know which one is correct? Cosmic microwave background. That's where the cosmic microwave background, or the CMB, comes in. The CMB is essentially the afterglow of the Big Bang, a faint radiation that fills the universe and serves as a kind of fossil record of the early universe. By studying tiny fluctuations in the CMB, scientists can learn about the distribution of matter and energy in the universe, which in turn gives clues about its shape. One of the key things scientists look for in the CMB is how evenly it's spread out. If the universe is flat, the temperature fluctuations in the CMB will appear evenly spaced and regular. If the universe is open or closed, those fluctuations will have a different pattern because of how space is curved. Based on current observations, the evidence suggests that the universe is very close to being flat. When scientists measure the curvature using the CMB, the numbers show that if there is any curvature, it's extremely small. So small that it falls within the margin of error for our instruments. This finding is significant because it suggests that the universe will continue expanding, but at a gradually slowing pace, without ever collapsing in on itself or ripping apart. It's not a perfect answer, though. While the universe seems flat within our observational limits, there's still the possibility that it could be slightly curved in a way we can't yet detect. Even a tiny amount of curvature, if present, could change the ultimate fate of the universe. What's also interesting is how these models tie into the concept of dark energy. Dark energy is a mysterious force that makes up about 70% of the universe's total energy content, and it's responsible for driving the acceleration of the universe's expansion. The presence of dark energy complicates the picture of the universe's future because it seems to be pushing space apart at an increasing rate, which could lead to an open universe scenario where the expansion goes on forever and eventually leads to a big rip. On the other hand, if dark energy behaves in a different way over time, it could slow down or even reverse its effect, leading to a closed universe and a big crunch. Right now, we don't fully understand the nature of dark energy, so it's hard to say for sure what the future holds. But what we do know is that the curvature of space plays a crucial role in shaping the destiny of the universe. Einstein's general relativity, the blueprint for warped space. Einstein's theory of general relativity changed how we think about space, time, and reality itself. Before Einstein, people thought of space as a fixed, unchanging backdrop, something where objects just existed and moved around. But Einstein showed that space isn't fixed at all. Instead, it's like a flexible fabric that can be stretched, bent, and warped by the things within it, by planets, stars, and even light. This idea completely rewrote our understanding of gravity, and by extension, the universe. At the heart of Einstein's theory are the Einstein field equations. These equations describe how space-time curves in response to mass and energy. The more massive an object, the more it warps the space around it. For example, Earth's mass causes a bend in space-time, which is why objects fall toward it, what we experience as gravity. But the equations also predict much stranger things, like black holes, places where space-time curves so sharply that nothing, not even light, can escape. These equations also predict something called gravitational waves. Gravitational waves are ripples in the fabric of space-time, created when massive objects like black holes collide. These ripples travel through space, stretching and squeezing it as they pass. It wasn't until 2015 that scientists were able to detect these waves directly, which was a major confirmation of Einstein's predictions. Gravitational waves aren't just a neat concept, they give us a new way of studying the universe. By detecting these ripples, we can learn about violent events like black hole collisions that are otherwise invisible to us. One of the earliest tests of general relativity came in 1919, just a few years after Einstein published his theory. British astronomer Sir Arthur Eddington led an expedition to observe a solar eclipse. During the eclipse, the sun's light was blocked, allowing scientists to observe the stars behind it. According to general relativity, the sun's gravity would bend the light from these stars, making them appear in slightly different positions than usual. And that's exactly what Eddington observed. The starlight was bent, confirming that gravity does indeed warp space-time. This was one of the first real-world proofs of general relativity, and it made Einstein a global sensation. The implications of general relativity aren't just theoretical. They affect our daily lives in ways we don't always notice. A perfect example of this is GPS. The global positioning system relies on satellites that orbit Earth and send signals to our devices, allowing them to pinpoint our location. But here's the catch. Those satellites are moving fast, and they're farther away from the Earth's gravitational pull than we are. According to general relativity, both of these factors cause time to move differently for the satellites than it does for us on the ground. The satellites experience time slightly faster than we do. Without adjusting for this time dilation, GPS signals would become inaccurate, causing location errors of several kilometers every day. So, every time you use GPS to get directions, you're benefiting from Einstein's theory of general relativity. Einstein's equations also had huge implications for our understanding of the universe as a whole. Before general relativity, most scientists thought of the universe as static and unchanging. But Einstein's equations suggested that the universe couldn't be static. It had to either be expanding or contracting. At first, Einstein was troubled by this idea and even added a cosmological constant to his equations to make the universe seem static. But in the 1920s, astronomer Edwin Hubble discovered that galaxies were moving away from each other, providing direct evidence that the universe is expanding. This was the birth of the Big Bang theory, the idea that the universe started from a single dense point and has been expanding ever since. Einstein later called the addition of the cosmological constant his biggest mistake. But the expansion of the universe brings up more questions. What will happen to the universe in the distant future? Will it expand forever? Will it eventually slow down and collapse back in on itself? The answers to these questions depend on several factors, including the amount of matter and energy in the universe and the properties of something called dark energy. Dark energy is a mysterious force that seems to be driving the acceleration of the universe's expansion. Right now, the evidence suggests that the universe will continue expanding indefinitely. But scientists are still trying to understand the true nature of dark energy. As mind-bending as general relativity is, it has its limitations. The theory works incredibly well when describing large objects like planets and stars, or when explaining things like the curvature of space-time. But when we try to apply general relativity to very small scales, like the inside of a black hole, or the very early moments of the Big Bang, the equations break down. This is where quantum mechanics comes into play. Quantum mechanics is the theory that describes the behavior of particles on the smallest scales, and it doesn't mesh well with general relativity. In fact, the two theories seem to describe two very different realities. This is one of the biggest unsolved problems in physics: how to reconcile general relativity with quantum mechanics. One of the strangest predictions of general relativity is the existence of singularities. A singularity is a point where space-time becomes infinitely curved, and the laws of physics as we know them no longer apply. Black holes contain singularities at their centers. At a singularity, gravity becomes so strong that space-time itself breaks down, and no one really knows what happens beyond that point. Singularities suggest that our understanding of the universe is incomplete. They're places where reality, as described by general relativity, seems to break. General relativity also changes the way we think about time. In the everyday world, we think of time as something that flows at a constant rate, the same for everyone, everywhere. But general relativity shows that time is relative. It depends on where you are and how fast you're moving. Time moves slower near massive objects like planets and stars, and it speeds up the farther you are from a source of gravity. This effect is known as gravitational time dilation, and it has been confirmed by experiments here on Earth. For example, clocks placed at higher altitudes, where gravity is slightly weaker, run faster than clocks at sea level. These differences are tiny, but they're measurable. Before Einstein, people thought of space and time as separate things. Space was where objects existed, and time was what kept everything moving. But general relativity shows that space and time are intertwined. When massive objects warp space, they warp time as well. This is why time slows down near a black hole or in a strong gravitational field. It's also why time seems to flow differently for astronauts on the International Space Station, who are moving quickly and are farther from the Earth's gravity. They age ever so slightly slower than people on Earth. Black holes, infinite curvature, and the collapse of reality. Black holes are some of the most mysterious and extreme objects in the universe. They stretch our understanding of physics and challenge the very nature of reality. When you think about black holes, you probably picture a dark, bottomless pit that pulls in everything around it, with no hope of escape. And while that's true to a large extent, the reality of black holes is even stranger than you might imagine. Black holes form when massive stars collapse under their own gravity, compressing all their mass into an incredibly small point. This results in a gravitational force so strong that not even light can escape once it crosses a certain boundary. But there's much more to black holes than just being cosmic vacuum cleaners. They're places where the laws of physics, as we know them, break down in some very fundamental ways. Understanding black holes isn't just about studying gravity, it's about exploring the limits of space, time, and reality itself. The point at which nothing can escape the pull of a black hole is known as the event horizon. This boundary marks the edge of the black hole, and once something crosses it, there's no going back. The event horizon is linked to a concept called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who first solved Einstein's equations for the simplest kind of black hole. The Schwarzschild radius is the distance from the center of a black hole to the event horizon, and it depends entirely on the black hole's mass. For example, if Earth were compressed into a black hole, its Schwarzschild radius would be about the size of a marble. The event horizon is not a physical surface. You wouldn't bump into it like a wall. It's just a point of no return. Beyond this point, space and time get so warped by the black hole's gravity that all paths lead inward, toward the center, where something even more bizarre awaits: the singularity. Singularities, where physics ceases to function. At the heart of every black hole, there lies a singularity, a point where matter is crushed down to infinite density. The strange thing about singularities is that despite being central to our understanding of black holes, and even the universe itself, we don't fully understand them. In a singularity, the density of matter becomes infinite. This means that all the mass of the black hole, or any object that collapses into a singularity, is compressed into a point with no volume. It's hard to wrap our heads around this idea because it doesn't fit into our everyday experience. In normal situations, no matter how much you compress something, it still takes up space. But at a singularity, that space vanishes. The gravitational pull becomes so strong that space-time curves infinitely, and nothing, not even light, can escape. And the laws of physics as we know them break down at a singularity. General relativity, which describes gravity and the behavior of massive objects, predicts the existence of singularities, but it can't tell us what happens inside them. This is because the equations of general relativity start to give us nonsensical answers when we try to apply them to a point of infinite density. Time itself seems to stop, and the very fabric of reality gets torn apart. This suggests that our current theories of physics are incomplete and can't fully describe what happens in these extreme environments. This is where the quest for a theory of quantum gravity comes into play. Right now, we have two major theories for understanding the universe: general relativity and quantum mechanics. General relativity works incredibly well when describing massive objects like stars and galaxies, while quantum mechanics explains the behavior of particles on the tiniest scales. But these two theories don't work well together. Singularities are where this conflict becomes especially clear. General relativity predicts that matter becomes infinitely dense at a singularity, But quantum mechanics doesn't allow for such infinite values. It suggests that there should be a limit to how much matter can be compressed. To bridge this gap, physicists are working to develop a theory of quantum gravity, a theory that would combine the principles of general relativity and quantum mechanics into a single framework. Such a theory would allow us to describe what happens at the singularities inside black holes, and even at the moment of the Big Bang. Unfortunately, no one has yet found a complete theory of quantum gravity, though approaches like string theory and loop quantum gravity are being actively explored. The cosmic censorship hypothesis is another interesting idea related to singularities. It was proposed by physicist Roger Penrose in the 1960s and suggests that singularities are always hidden from the rest of the universe by an event horizon, the boundary surrounding a black hole from which nothing can escape. According to this hypothesis, singularities can't be naked, meaning they can't be exposed to the rest of the universe without being shielded by an event horizon. In simple terms, the hypothesis protects the universe from the chaos and breakdown of physics that occurs at singularities, keeping them safely tucked away inside black holes where they can't affect the outside world. However, the cosmic censorship hypothesis is just that, a hypothesis. It's an idea that hasn't been proven or disproven. There are some theoretical scenarios where singularities might not be hidden behind event horizons. These so-called naked singularities would be exposed to the universe, potentially causing all kinds of problems for our understanding of physics. If such singularities exist, they could represent places where the normal laws of cause and effect break down, creating unpredictable and possibly dangerous consequences. For now, though, there's no direct evidence for naked singularities, and most black holes seem to follow the rules laid out by the cosmic censorship hypothesis. Singularities also play a crucial role in our understanding of the early universe. Just as there's a singularity at the center of every black hole, there was a singularity at the very beginning of the universe, at the moment of the Big Bang. The Big Bang theory tells us that the universe started from an incredibly hot, dense state and has been expanding ever since. But before this expansion began, the entire universe was compressed into a point of infinite density, a singularity, just like those found in black holes. This Big Bang singularity is another place where the laws of physics break down. At such high densities and temperatures, general relativity no longer works, and we don't have a good theory for what happened in the earliest moments of the universe. Just like with black hole singularities, understanding the Big Bang singularity requires a theory of quantum gravity. Such a theory could help explain how the universe emerged from this initial state of infinite density, and give us a clearer picture of what happened in the first fraction of a second after the Big Bang. The existence of singularities also raises questions about the nature of space-time itself. Singularities represent points where space-time becomes so warped that our usual understanding of space and time ceases to exist. Inside a black hole, for example, time itself comes to a standstill as you approach the singularity. This is because the gravitational pull becomes so strong that the normal flow of time is distorted beyond recognition. Space and time get tangled up in ways that are hard to imagine, and the distinction between the two begins to blur. The breakdown of space-time at singularities suggests that space and time aren't as stable or fundamental as we once thought. In our everyday lives, we experience space and time as fixed, unchanging dimensions. But singularities show us that under extreme conditions, these dimensions can collapse and fall apart. This has led some physicists to speculate that space and time might be emergent properties, meaning they arise from deeper, more fundamental processes that we don't yet understand. In other words, space and time might not be the basic building blocks of reality, but instead they could emerge from something even more fundamental. The information paradox. When something falls into a black hole, whether it's a star, a planet, or even a simple particle, it passes beyond the event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull. Once something crosses the event horizon, it's lost to the outside universe forever. The question that physicists have been grappling with for decades is this: what happens to the information about the things that fall into a black hole? Does it get destroyed, or is there some way for that information to be preserved? This question creates a paradox because in the world of quantum mechanics, information must always be conserved. This means that the total amount of information in the universe should remain constant over time. Even if you burn a book, for example, the information that made up the book isn't lost. It might be transformed into heat, smoke, and ash. But the fundamental information about the atoms and molecules that made up the book still exists, even if it's scattered. But black holes seem to break this rule. Anything that falls into a black hole appears to vanish completely, leading to the possibility that the information about those objects is destroyed. This is the heart of the information paradox. The idea that information could be destroyed in a black hole conflicts with quantum mechanics, which insists that information must be conserved. This conflict has led to decades of debate and has challenged our understanding of both quantum mechanics and general relativity, the theory that describes the behavior of massive objects like black holes. One of the leading figures in this debate was physicist Stephen Hawking, who made some of the earliest and most influential contributions to our understanding of black holes and the information paradox. In 1974, Hawking made a groundbreaking discovery. Black holes aren't entirely black. He predicted that they emit a faint form of radiation, now known as Hawking radiation. This radiation arises from quantum effects near the event horizon of the black hole. Essentially, pairs of particles are created just outside the event horizon. One particle falls into the black hole while the other escapes into space. Over time, this process causes the black hole to lose mass and shrink. If Hawking's theory is correct, then black holes will eventually evaporate entirely, releasing all of their mass as radiation. This process raises an interesting question about the fate of the information contained within the black hole. If the black hole evaporates, does that mean the information about everything that fell into it is lost forever? Hawking initially suggested that the information is indeed lost, which would mean that black holes fundamentally violate the rules of quantum mechanics. This idea sparked a heated debate among physicists and led to what became known as the black hole information paradox. At first glance, it might seem that Hawking radiation could carry the information about the objects that fell into the black hole. But there's a problem. Hawking radiation is completely random. It doesn't seem to carry any information about the matter that originally fell into the black hole. If all the information is encoded in the random radiation that the black hole emits as it evaporates, then that information is essentially lost forever, scrambled beyond recognition. This idea didn't sit well with many physicists, who were reluctant to accept the idea that information could be destroyed. Over time, alternative theories emerged in an attempt to resolve the paradox. Some physicists proposed that the information might not be lost after all, but rather, it could be encoded in a highly scrambled form in the Hawking radiation. This is similar to how the information in a burned book isn't destroyed. It's just scattered and difficult to reconstruct. But the challenge with this idea is that Hawking radiation is so random that it's unclear how the information could be recovered, even in principle. If the information is so thoroughly scrambled that it can never be reconstructed, does that really count as information conservation? The paradox remains unresolved in this scenario. Another approach to solving the information paradox involves the concept of complementarity. According to this idea, there is no need to choose between information being destroyed or preserved. Both could be true, depending on how you look at the black hole. From the perspective of an observer outside the black hole, the information is never truly lost. It's just encoded in a complex way near the event horizon. However, from the perspective of someone who falls into the black hole, the information seems to disappear into the singularity at the center. This dual perspective allows for both information conservation and Hawking's theory of black hole evaporation to coexist, though it still leaves many open questions. In recent years, yet another potential solution has emerged, involving something called the holographic principle. This idea, which comes from string theory, suggests that all the information about the contents of a black hole might be stored on its surface rather than inside the black hole itself. This is similar to a hologram, where a three-dimensional image is encoded on a two-dimensional surface. If the holographic principle is correct, then the information about everything that falls into a black hole could be encoded on its event horizon, and this information could be preserved even as the black hole evaporates. This would resolve the paradox by ensuring that no information is ever truly lost. It's just stored in a different way than we might expect. The holographic principle has gained a lot of attention because it offers a way to reconcile quantum mechanics with the behavior of black holes. But like many ideas in theoretical physics, it's still speculative, and more work is needed to fully understand how it might resolve the information paradox. In 2019, a breakthrough came when physicists studying black hole entropy, the measure of the disorder of a system, found that certain quantum corrections to Hawking's original calculations might allow information to escape from a black hole in a more orderly way than previously thought. This research has brought renewed hope that the information paradox might one day be solved, but it's far from a definitive answer. Now, the idea that black holes can evaporate leads us to another mind-bending concept: black hole thermodynamics. Black hole thermodynamics. It may sound strange to think of black holes as having a temperature, but they do. According to Hawking's theory, the smaller the black hole, the hotter it gets, while massive black holes like the ones at the centers of galaxies are extremely cold. Smaller black holes could theoretically become incredibly hot just before they disappear entirely. Black holes also have entropy, a measure of the amount of disorder or randomness in a system. This is where things get really weird. The entropy of a black hole isn't proportional to its volume as you might expect, but to the surface area of its event horizon. This finding has led some scientists to speculate that all the information about what falls into a black hole is encoded on its surface, much like a hologram. If true, this idea could have profound implications for our understanding of the universe and might hint at a deeper connection between gravity, thermodynamics, and quantum mechanics. Black holes aren't just theoretical objects, they're real, and we can detect them in a variety of ways. One of the most exciting ways we've observed black holes recently is through gravitational waves. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, like black holes colliding. When two black holes merge, they send out these waves, which travel across the universe. In 2015, scientists detected gravitational waves for the first time, a discovery that confirmed another prediction of Einstein's theory of general relativity. The detection of gravitational waves is a game-changer for astronomy. Before, we could only observe black holes indirectly by watching how they affect nearby stars and gas. But now, we can listen to black holes as they collide and merge, giving us a new way to study these mysterious objects. Each time we detect gravitational waves, we learn more about the properties of black holes, including their masses, spins, and how they interact with each other. These observations provide us with direct evidence of black holes and offer new insights into the nature of space-time itself. Gravitational waves also give us a way to test the limits of general relativity. Einstein's theory has been incredibly successful in describing the universe on large scales, but it hasn't been tested in the extreme environments near black holes. Black holes challenge our understanding of the universe in so many ways. They reveal the limits of our current theories and force us to confront questions about the nature of reality itself. What happens inside a singularity? Can information be truly destroyed? How does gravity fit into the quantum world? These are some of the biggest mysteries in physics, and black holes might hold the key to answering them. In a way, black holes represent the ultimate frontier of human knowledge. They are places where the rules of physics, space, and time collapse in on themselves. And yet, they're also places where we can push the boundaries of what we know, exploring the deepest questions about the nature of reality. Whether it's through the detection of gravitational waves, the study of black hole thermodynamics, or the ongoing quest to solve the information paradox, black holes continue to captivate scientists and challenge our understanding of the universe. When expanding space threatens to tear existence, while inflation itself is a well-established theory, it opens the door to some mind-bending ideas, including the possibility of a multiverse. The rapid growth of space during inflation not only answers many questions about the early universe, but also raises new ones about the nature of existence itself. In the first moments after the Big Bang, the universe was in a hot, dense state, much smaller than we see it today. The theory of cosmic inflation suggests that, within the first trillionth of a second, the universe expanded exponentially. This expansion happened at a rate much faster than the speed of light, causing space to grow by an unfathomable amount in an extremely short time. To put this into perspective, imagine something as small as a proton suddenly expanding to the size of a galaxy. This is the kind of mind-blowing growth that inflation represents. The concept of cosmic inflation was first introduced by physicist Alan Guth in 1980, and it provides answers to several long-standing puzzles about the universe. One of the key problems it addresses is the so-called horizon problem. In simple terms, the horizon problem refers to the fact that different parts of the universe appear to be nearly identical in temperature and structure, even though they should be too far apart to have ever influenced each other. Without inflation, it's hard to explain how these regions of the universe could have become so similar, since there simply wasn't enough time for light, or any information, to travel between them before they expanded to their current size. Inflation solves this problem by suggesting that before the rapid expansion, the universe was small enough for all regions to be in close contact. As space expanded during inflation, these regions were stretched far apart, but they retained the similarities that formed when they were much closer together. This explains why the universe looks so uniform on large scales, even though its different parts are now separated by billions of light years. Inflation also smooths out the universe in another important way. Without it, we might expect the universe to be lumpy and uneven, with areas of wildly different densities. But inflation stretches out any irregularities, leaving the universe smooth and homogeneous on large scales. This explains why, even though the universe contains vast structures like galaxies and clusters of galaxies, it appears relatively uniform when viewed from a distance. But inflation does more than just smooth out the early universe. It also plays a key role in the formation of the galaxies and structures we see today. During the inflationary period, tiny quantum fluctuations, essentially random, microscopic variations in energy, were stretched to enormous sizes. These fluctuations, which started out as tiny blips at the quantum level, were blown up to cosmic scales by the rapid expansion of space. Over time, they acted as the seeds for the formation of galaxies, stars, and other structures in the universe. Despite its incredible speed and power, cosmic inflation didn't last long. It came to an end after just a tiny fraction of a second, but what happened next was crucial for shaping the universe as we know it. As inflation ended, the energy that had driven the rapid expansion was released, leading to a period known as reheating. During reheating, the universe became filled with particles and radiation, marking the beginning of the hot, dense state that we associate with the early universe. Reheating is also when the particles and forces that make up our universe, the ones described by the standard model of particle physics, came into being. During this process, the universe transitioned from the strange inflationary state into a more familiar one, filled with the kinds of particles that eventually formed atoms, stars, and galaxies. Without reheating, the universe would have remained an empty, cold expanse of space. But this phase kick-started the processes that eventually led to the formation of everything we see today. While inflation ended in our observable universe, the theory suggests that inflation might never have fully stopped. In fact, one of the most intriguing ideas to come out of inflationary theory is the concept of an inflationary multiverse. The idea here is that, while inflation ended in our region of the universe, it might continue in other regions. According to this view, different pockets of space could undergo inflation at different times, creating separate universes with their own physical laws and properties. In this inflationary multiverse, each pocket universe could be radically different from the others. Some might have different laws of physics, while others could have different fundamental constants, such as the strength of gravity or the charge of the electron. This would mean that the universe we observe is just one of many, each with its own unique properties. While this idea remains speculative, it's an intriguing possibility that extends the implications of inflation far beyond our observable universe. The concept of the inflationary multiverse also ties into the idea of eternal inflation. According to this theory, while inflation ends in some regions, it continues indefinitely in others. As a result, new universes are constantly being created in different parts of the multiverse. This idea challenges our understanding of reality itself, suggesting that what we consider the universe is just one small part of a much larger and more complex system of interconnected universes. The holographic principle. Is our universe a projection? This idea suggests that our three-dimensional universe might be a projection of information stored on a two-dimensional surface. It's an incredibly challenging notion because it defies the way we naturally think about space and reality. To understand where this idea comes from and what it might mean for our understanding of the universe, we have to delve into the holographic hypothesis and how it ties into some of the most fundamental aspects of black holes, entropy, and cosmology. The holographic hypothesis, first proposed by physicists Gerard 't Hooft and Leonard Susskind in the 1990s, is a bold attempt to reconcile certain puzzles in physics, particularly related to black holes. The central idea is that all the information about a volume of space can be encoded on a lower dimensional boundary, similar to how a hologram works. In a hologram, a 2D image can create the illusion of a 3D object. Likewise, the holographic principle suggests that the entire universe we experience in 3 dimensions might actually be the result of information stored on a distant 2-dimensional boundary, possibly at the edge of the universe itself. This theory challenges our basic understanding of reality. We're used to thinking of the world as a 3-dimensional space in which objects have length, width, and depth. However, if the holographic principle is correct, these 3 dimensions could be nothing more than a projection from a lower dimensional space. It's a radical departure from the way we normally perceive the universe, but it's not without theoretical support. One of the key motivations for the holographic principle comes from the study of black holes. Black holes have long been a source of fascination for physicists because they push the laws of physics to their limits. At the center of a black hole lies a singularity, a point where matter is compressed to infinite density and the laws of physics break down. Surrounding the black hole is the event horizon, the point beyond which nothing, not even light, can escape the black hole's gravitational pull. In the 1970s, physicist Jacob Bekenstein made a remarkable discovery. The entropy of a black hole isn't proportional to its volume, as you might expect, but to the surface area of its event horizon. Entropy is a measure of the amount of disorder or randomness in a system, and in most systems, entropy scales with the volume. But for black holes, entropy scales with the surface area of the event horizon, suggesting that all the information about what has fallen into the black hole is somehow encoded on its surface, rather than inside its volume. This finding was later supported by Stephen Hawking's discovery that black holes emit radiation, now known as Hawking radiation, and slowly lose mass over time. Hawking's calculations showed that as a black hole radiates energy and shrinks, its entropy decreases in proportion to the surface area of its event horizon, not its volume. This curious relationship between entropy and area led to the idea that the information about everything that falls into a black hole is stored on its surface. The implications of this are profound. If all the information about the contents of a black hole is encoded on its surface, could the same be true for the universe as a whole? Could it be that everything we experience in 3 dimensions is actually encoded on a 2-dimensional boundary, like a cosmic hologram? This is the heart of the holographic principle. One way to think about this is to imagine the universe as a giant 3D projection, like the image produced by a hologram. Just as a hologram encodes a 3D image on a 2D surface, the holographic principle suggests that all the information in our 3D universe might be encoded on a distant 2D surface. This surface could be the boundary of the universe, something far beyond the edge of our observable universe, possibly linked to the universe's expansion. The idea that the universe is a projection from a 2D surface is not only mind-boggling, but it also has deep implications for cosmology. If our universe is truly holographic, it could mean that space and time themselves are emergent properties, something that arises from more fundamental processes happening on this distant 2D boundary. This could change how we think about the nature of reality itself. What we experience as physical objects and events might be the result of processes occurring far beyond our view, projected into our perception of 3D space. One of the reasons this idea has gained traction in theoretical physics is because it offers a potential solution to the black hole information paradox. The paradox arises from the apparent contradiction between quantum mechanics and general relativity when it comes to black holes. Quantum mechanics tells us that information about a system can never be destroyed, while general relativity suggests that anything that falls into a black hole is lost forever once it crosses the event horizon. If the holographic principle is correct, however, the information isn't lost, it's just stored on the surface of the black hole, much like a hologram stores information about a 3D image on a 2D surface. This idea could preserve the integrity of quantum mechanics while still allowing for black holes to behave as predicted by general relativity. But the implications of the holographic principle go beyond black holes. If the entire universe is holographic, it suggests that all of the information about the universe, including the positions and properties of every particle and field, could be encoded on a distant boundary. This idea is closely related to a branch of physics known as string theory, which attempts to unify quantum mechanics and general relativity. In string theory, the holographic principle plays a key role in understanding how gravity works in higher dimensions. Some versions of string theory propose that our universe exists on a 3D brane, short for membrane, that floats in a higher dimensional space, with the information about our universe encoded on a 2D boundary. This leads to an even more radical question. Is the universe itself an illusion? Could it be that what we perceive as solid 3-dimensional reality is actually a projection from something deeper and more fundamental? If space and time are emergent properties, as the holographic principle suggests, then the very fabric of reality might not be what it seems. The objects and events we observe could be the result of information processing happening on the distant edges of the universe. Dark energy, the force pushing space beyond its limits. Dark energy is one of the most mysterious and fascinating concepts in modern cosmology. It's a force that seems to be pushing the universe apart, accelerating its expansion, and defying our expectations about how the universe should behave. The discovery of dark energy has transformed our understanding of the cosmos and raised profound questions about the ultimate fate of the universe. Despite its immense influence, we know very little about what dark energy actually is, and its discovery has led to new theories about how the universe could end, including the terrifying prospect of a Big Rip. The story of dark energy begins with the discovery that the universe is expanding. This idea was first proposed by astronomer Edwin Hubble in the 1920s. Hubble's observations showed that distant galaxies were moving away from us. suggesting that the universe was getting larger over time. At the time, most scientists assumed that while the universe was expanding, the force of gravity would eventually slow this expansion down. They expected that over time, the expansion would decelerate, perhaps even halting altogether, leading to a static universe, or in some models, causing the universe to collapse back in on itself. However, in the late 1990s, two independent teams of astronomers made a shocking discovery. The expansion of the universe wasn't slowing down, it was speeding up. By studying the light from distant supernovae, these scientists found that the universe's expansion had been accelerating for billions of years. This discovery turned cosmology on its head. If the universe was expanding faster and faster, there had to be some kind of force driving this acceleration, something that could counteract the pull of gravity. This mysterious force became known as dark energy. Dark energy is believed to make up around 70% of the universe's total energy content. It's an incredibly powerful force, but we don't know what it is or where it comes from. Unlike gravity, which pulls objects toward each other, dark energy seems to have the opposite effect. It pushes everything apart. One way to think about it is that dark energy acts like an anti-gravity force, causing galaxies to move away from each other at ever-increasing speeds. The discovery of dark energy has forced scientists to rethink their models of the universe. Before its discovery, the prevailing view was that the universe would either expand forever at a steady rate, or eventually collapse in on itself due to gravity. But dark energy changes everything. Now, it seems that the universe will continue to expand faster and faster, and this has dramatic implications for the future of the cosmos. One of the most striking aspects of dark energy is how little we know about it. We can measure its effects on the expansion of the universe, but we don't know what it's made of or how it works. Some scientists have suggested that dark energy could be a property of space itself. In this view, as space expands, more dark energy is created, driving further expansion in a feedback loop. Others have proposed that dark energy might be related to the cosmological constant, a term that Einstein introduced in his equations of general relativity to represent a force that counteracts gravity and keeps the universe from collapsing. Einstein later called the cosmological constant his biggest blunder after Hubble's discovery of the expanding universe. But it now seems that this idea might have been closer to the truth than even Einstein realized. Another possibility is that dark energy is related to a new field or particle that we haven't yet discovered. In this case, dark energy might behave differently over time, perhaps becoming stronger or weaker as the universe evolves. Some theories suggest that dark energy could eventually fade away, while others propose that it might become even more dominant in the future, with catastrophic consequences for the universe. The discovery of dark energy has led to new theories about how the universe could end. One of the most dramatic possibilities is known as the Big Rip. In this scenario, dark energy continues to accelerate the expansion of the universe at an ever-increasing rate. As the expansion speeds up, galaxies, stars, planets, and even atoms themselves would be torn apart by the overwhelming force of dark energy. To understand how the Big Rip works, it's helpful to think about how gravity and dark energy interact. Right now, galaxies are held together by gravity, which counteracts the expansion of the universe on smaller scales. This is why galaxies and galaxy clusters don't expand along with the universe. Gravity is strong enough to keep them bound together. However, if dark energy continues to accelerate the expansion of the universe, there could come a point where it overwhelms the force of gravity. When this happens, even tightly bound systems like galaxies, stars, and planets would be ripped apart by the expanding space around them. In the Big Rip scenario, the expansion of the universe would become so rapid that it would eventually tear apart everything, right down to the smallest scales. Galaxies would be the first to go, followed by solar systems, individual stars, and planets. As dark energy continues to dominate, even atoms and subatomic particles would be pulled apart. The universe would be left as a cold, empty void, with no matter, no energy, and no structure, just an endless, expanding nothingness. The idea of a big rip is terrifying, but it's important to remember that this is just one possible outcome. The future of the universe depends on the nature of dark energy, and we still don't fully understand what dark energy is, or how it will behave in the long term. If dark energy is constant, as it appears to be right now, the universe will likely continue to expand forever, but at a slower rate than the Big Rip scenario suggests. In this case, galaxies would continue to drift apart, and over trillions of years, the universe would become a cold, dark place as stars burn out and galaxies fade away. This scenario is often referred to as the Big Freeze, where the universe eventually reaches a state of maximum entropy, with no energy left to fuel stars or other cosmic processes. There are other, more speculative ideas about how dark energy could shape the end of the universe. One possibility is that dark energy might weaken or even reverse in the future, causing the expansion of the universe to slow down or stop. If this happens, gravity could take over once again, pulling everything back together in a big crunch. In this scenario, the universe would collapse in on itself, returning to the hot, dense state from which it emerged in the Big Bang. Some theories suggest that the universe could undergo cycles of expansion and contraction, with each big crunch followed by another Big Bang. Another possibility is that dark energy could lead to the formation of new universes. Some theories in cosmology suggest that our universe might be part of a multiverse, a vast collection of universes, each with its own laws of physics and properties. In this view, dark energy could play a role in the creation of new universes, with different regions of space expanding at different rates, leading to the formation of pocket universes, with their own distinct characteristics. This idea is highly speculative, but it raises intriguing questions about the nature of reality and the possibility of other universes beyond our own. Despite the many mysteries surrounding dark energy, one thing is clear. It plays a crucial role in shaping the fate of the universe, whether it leads to a big rip, a big freeze, or some other outcome. Dark energy will determine how the universe evolves in the future. For now, the discovery of dark energy has given us a new understanding of the cosmos and forced us to confront questions about the ultimate fate of the universe. How bending space warps the flow of time. Time, which we often think of as flowing uniformly for everyone and everything, can actually be stretched, slowed down, or even nearly stopped depending on certain factors like gravity and velocity. In short, time doesn't behave the way we're used to when space bends or when objects move at incredible speeds. Let's dive into how bending space warps the flow of time and how time dilation manifests itself in various situations, from Earth to the extreme environments of black holes. Gravitational time dilation, a prediction of Einstein's general theory of relativity, occurs in the presence of a strong gravitational field. General relativity tells us that massive objects like planets and stars curve the fabric of space-time, and this curvature affects the flow of time. The stronger the gravitational pull, the more space-time is warped, and the slower time moves in that region compared to a place with weaker gravity. To understand this concept more concretely, let's look at an example close to home: clocks on Earth versus those in orbit. On Earth's surface, we're relatively close to the planet's center of gravity, where the gravitational field is strong. However, clocks aboard satellites, which orbit high above the Earth where gravity is weaker, tick slightly faster than those on the ground. This isn't just a theoretical prediction, it's a well-documented effect. For instance, the Global Positioning System, GPS, which we rely on for navigation, takes gravitational time dilation into account. The satellites that make up the GPS network orbit about 20,000 kilometers above Earth. At that altitude, time runs a little faster due to the weaker gravitational pull. If GPS systems didn't correct for this difference, they would be off by several kilometers per day, rendering them virtually useless for accurate navigation. The idea that time can be warped by gravity becomes even more extreme when we consider highly massive objects like black holes. Near a black hole, the gravitational pull is so intense that time slows down significantly. As you approach a black hole's event horizon, the point of no return where not even light can escape, time dilation becomes so extreme that, to a distant observer, time appears to almost stop. For someone far from the black hole, an object falling towards the event horizon would seem to slow down and never quite cross it. From the perspective of the object, though, time would seem to pass normally, but once they crossed the event horizon, they would be lost to the outside universe forever. This extreme time dilation near black holes is one of the strangest predictions of general relativity, and has been the subject of much fascination in both scientific and popular discussions about space and time. The idea that time could essentially freeze at the boundary of a black hole challenges our everyday understanding of how time works. Another form of time dilation, known as relativistic time dilation, arises from special relativity, Einstein's earlier theory that deals with the behavior of objects moving at high speeds. According to special relativity, time slows down for objects as they approach the speed of light. The faster something moves, the more pronounced this effect becomes. This means that a clock on a spaceship traveling at nearly the speed of light would tick much more slowly compared to a clock on Earth. Let's imagine a scenario where astronauts travel to a distant star at a speed close to that of light. For the people on board the spaceship, time would pass more slowly than for people back on Earth. A journey that feels like a few years for the astronauts might translate into decades or even centuries for those who stayed behind. This is because, at such high speeds, the passage of time becomes stretched out due to relativistic time dilation. The classic thought experiment, known as the twin paradox, illustrates this concept. In the twin paradox, one twin remains on Earth, while the other twin travels into space at near light speed. When the spacefaring twin returns to Earth, they find that their sibling has aged significantly more than they have. This paradox highlights how the passage of time depends on relative motion, and it has been confirmed by experiments. One of the most famous confirmations of time dilation comes from experiments involving atomic clocks. In 1971, scientists placed highly precise atomic clocks on airplanes and flew them around the world, comparing the time they kept with identical clocks that stayed on the ground. The clocks on the airplanes, which were moving at high speeds relative to the clocks on Earth, showed a slight but measurable slowing of time. This experiment was a direct confirmation of relativistic time dilation, and it demonstrated that even at the speeds we can achieve with airplanes, the effects of time dilation are real. Similarly, satellites in orbit experience both gravitational time dilation and relativistic time dilation. The combined effect of these two forms of time dilation is taken into account for GPS and other satellite-based systems, ensuring that they remain accurate despite the small but significant differences in the passage of time. Time dilation isn't just a curiosity confined to theoretical physics labs and science fiction stories. It also plays a crucial role in cosmology. One of the most intriguing examples of time dilation in the universe comes from distant galaxies and the light they emit. Because the universe is expanding, light from objects billions of light years away is stretched, a phenomenon known as cosmological time dilation. As space itself expands, the wavelengths of light coming from distant galaxies are stretched, causing the light to appear redshifted. This redshift is not just a shift in color, it's also a shift in time. The farther away a galaxy is, the more its light is stretched, and the slower its time appears to pass from our perspective. This effect is particularly noticeable when we observe distant supernovae. A supernova is the explosive death of a star, and the light it emits follows a predictable pattern. However, when we observe supernovae in distant galaxies, we see that their light curves, the way their brightness changes over time, are stretched out, taking longer to rise and fall. This is a direct result of cosmological time dilation. Because the universe has expanded since the light from these distant objects was emitted, the passage of time appears slower for them compared to objects closer to us. Quantum fluctuations at the foundation of reality. At the smallest scales of the universe, far below the level of atoms and particles, lies a realm where our everyday understanding of space and time no longer holds. In this realm, space and time themselves are not continuous and smooth as they appear to us, but rather consist of a chaotic, ever-shifting structure known as space-time foam. This concept, introduced by physicist John Wheeler in the 1950s, suggests that at extremely small scales, specifically the Planck scale, space-time is a seething, frothy mess of quantum fluctuations. These fluctuations happen so rapidly and at such small scales that they give rise to the idea that space-time itself is constantly bubbling, fluctuating, and churning at the foundation of reality. To understand what space-time foam really is, we first need to grasp the significance of the Planck scale. The Planck length, which is about 1.6 × 10 circumflex 35 meters, represents the smallest meaningful unit of distance. Below this scale, the concepts of space and time as we know them break down due to the effects of quantum uncertainty. This is the realm where quantum mechanics takes over, and our familiar notions of geometry, distance, and time become fuzzy and uncertain. At the Planck scale, the smooth continuum of space-time, predicted by general relativity, gives way to a foam-like structure filled with tiny bubbles of space-time, which constantly appear and disappear. These quantum fluctuations are the result of the uncertainty principle, a cornerstone of quantum mechanics that tells us we can never know certain properties of a system, such as position and momentum, exactly at the same time. In the case of space-time foam, this uncertainty applies to space and time themselves. As a result, at incredibly small scales, space-time is no longer a fixed backdrop for events. Instead, it becomes a dynamic, shifting entity where space and time fluctuate unpredictably. This constant flux leads to the formation of tiny, ephemeral structures, such as microscopic black holes and wormholes, that pop in and out of existence, destabilizing space-time at the most fundamental level. These fluctuations are far too small to be observed directly, but their existence is predicted by quantum mechanics. At the Planck scale, the energy levels of these quantum fluctuations are so high that they can briefly create tiny black holes, each of which exists for only a fleeting moment before disappearing again. These miniature black holes are nothing like the massive, stable black holes we observe in space. Instead, they are fleeting events that exist only due to the extreme energy levels found at the quantum scale. Similarly, these fluctuations could also give rise to microscopic wormholes, tiny tunnels through space-time that could connect different regions of the universe, if only for a fraction of a second. The idea that space-time itself could be filled with these tiny, fleeting structures is mind-bending. It suggests that at the most fundamental level, space-time is not a smooth continuum, but rather a frothy, turbulent sea of quantum activity. These fluctuations make space and time fuzzy at the smallest scales, meaning that it becomes impossible to measure distances or durations with absolute precision. This fuzziness blurs the distinction between space and time, making both less distinct and more intertwined at these scales. One of the most profound implications of space-time foam is that it challenges our understanding of the nature of reality. If space-time itself is fluctuating and uncertain, then the very foundation of our universe is built on a framework that is constantly shifting and unstable. This idea flies in the face of classical physics, where space and time are thought to provide a stable, unchanging backdrop for events to unfold. In the world of space-time foam, however, this stability disappears, leaving us with a picture of the universe that is far more chaotic and unpredictable. Space-time foam also plays a crucial role in the ongoing search for a theory of quantum gravity. Quantum gravity is the long-sought theory that aims to unify quantum mechanics, which governs the behavior of particles and forces on the smallest scales, with general relativity, which describes gravity and the behavior of massive objects on large scales. These two theories are incredibly successful in their respective domains, but they are fundamentally incompatible with each other. General relativity treats spacetime as a smooth continuum that can be bent and curved by the presence of mass and energy. Quantum mechanics, on the other hand, describes a world of probabilities, uncertainty, and discrete quantities. Spacetime foam provides a glimpse into how these two theories might come together. At the Planck scale, where spacetime fluctuations dominate, the effects of both quantum mechanics and gravity become equally important. Understanding how spacetime behaves at this scale is key to developing a theory of quantum gravity. The idea is that spacetime foam could represent the quantum behavior of spacetime, revealing how gravity behaves in the quantum realm, and offering clues about how to reconcile the two theories. One of the main challenges in developing a theory of quantum gravity is that the mathematical frameworks of quantum mechanics and general relativity are so different. Quantum mechanics deals with discrete, quantized quantities, while general relativity describes smooth, continuous spacetime. Spacetime foam suggests that spacetime might not be continuous at the smallest scales, but instead consists of discrete, fluctuating structures. This idea opens up the possibility that spacetime itself could be quantized, meaning that space and time might exist in discrete units, similar to how energy is quantized in quantum mechanics. String theory, one of the leading candidates for a theory of quantum gravity, offers a way to understand spacetime foam. In string theory, the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings exist in a higher dimensional space, and their vibrations give rise to the particles and forces we observe in the universe. At the Planck scale, spacetime is thought to emerge from the interactions of these strings, with spacetime foam representing the fluctuating behavior of spacetime in this higher dimensional framework. Loop quantum gravity, another approach to quantum gravity, also provides insights into spacetime foam. In this theory, spacetime is composed of discrete loops of quantum fields, which form a network that gives rise to the fabric of spacetime. At the Planck scale, these loops fluctuate, leading to the foam-like structure of spacetime. Loop quantum gravity suggests that spacetime is not a continuous fabric, but rather a network of interconnected quantum loops, which constantly change and evolve. Both of these theories offer possible explanations for the existence of spacetime foam, but neither has been definitively proven. The challenge of directly observing spacetime foam remains immense. The Planck scale is so small that it is far beyond the reach of current technology. However, some scientists hope that indirect evidence of spacetime foam might be found through its effects on high-energy cosmic rays, or in the behavior of light traveling over vast cosmic distances. For example, spacetime foam could cause tiny distortions in the paths of light from distant galaxies, leading to observable effects in the cosmic microwave background radiation or in the light from distant quasars. Fault lines in the fabric of the universe. These hypothetical, one-dimensional objects could stretch across vast distances in space, possessing incredible mass and energy. Although we have yet to detect them directly, cosmic strings have long been proposed as relics from the early universe, possibly emerging from phase transitions that occurred shortly after the Big Bang. If they do exist, their immense gravitational effects could provide us with new insights into the nature of spacetime, the formation of large-scale structures in the universe, and even fundamental physics. The search for cosmic strings continues to this day, with scientists looking for evidence in gravitational waves, cosmic microwave background radiation, and other astrophysical phenomena. The idea of cosmic strings was first introduced in the 1970s, as physicists tried to understand what might have happened during the rapid expansion and cooling of the universe in its earliest moments. As the universe expanded and cooled after the Big Bang, it underwent several phase transitions, similar to how water transitions between ice, liquid, and vapor. These phase transitions could have created topological defects in the structure of spacetime, and cosmic strings are one such defect. These strings are thought to be incredibly thin, perhaps as small as a proton in width, but they are immensely long, possibly stretching across galaxies or even the entire universe. Despite their thinness, cosmic strings would contain a tremendous amount of mass and energy, making them extremely powerful gravitational sources. At their core, cosmic strings are believed to be one-dimensional objects. Unlike particles, which are zero-dimensional points, or membranes, which are two-dimensional surfaces, cosmic strings are one-dimensional filaments that extend through space like infinitely long wires. The immense energy density of these strings comes from the tension along their length, much like how a tightly stretched rubber band contains potential energy. The tension in a cosmic string is thought to be so great that even a small segment of it could have the mass of a large planet. If they exist, cosmic strings would warp the fabric of space-time around them, creating significant gravitational effects. One of the most striking features of cosmic strings is their ability to bend space-time. According to Einstein's theory of general relativity, massive objects cause space-time to curve, and cosmic strings would be no exception. However, because cosmic strings are so narrow, the way they bend space-time is quite different from the way a planet or a star does. Instead of creating a spherical distortion, cosmic strings would create a conical distortion in space-time. This is often described as a deficit angle, where space around the string is slightly pinched together, creating a wedge-like effect. This bending of space-time around a cosmic string could lead to several observable effects, the most notable of which is gravitational lensing. Gravitational lensing occurs when light from a distant object, such as a galaxy or star, passes near a massive object on its way to Earth. The gravity of the massive object bends the path of the light, causing the distant object to appear distorted or duplicated. If a cosmic string were to pass in front of a distant galaxy, it could create a very distinctive lensing pattern, such as multiple identical images of the same galaxy or unusual arcs of light. This lensing effect could provide a way to detect cosmic strings, as their gravitational effects on light would be unmistakable. In addition to gravitational lensing, cosmic strings could also produce detectable gravitational waves. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, and they were first detected in 2015 when two black holes merged. Cosmic strings, with their immense energy and tension, could create gravitational waves in several ways. For example, if two cosmic strings were to collide, or if a single string formed a loop and collapsed, the resulting disturbance in spacetime could generate gravitational waves. These waves would propagate through the universe and could potentially be detected by observatories such as LIGO, Laser Interferometer Gravitational Wave Observatory, or future gravitational wave detectors. The formation of cosmic strings is thought to have occurred during phase transitions in the early universe. As the universe expanded and cooled in the moments after the Big Bang, it likely underwent several transitions where different physical forces and fields froze out, similar to how water freezes into ice. During these transitions, the symmetry of the universe broke in specific ways, creating defects in the structure of spacetime. Cosmic strings are one such defect, much like how cracks form in ice as it freezes. These strings would have been stretched across the rapidly expanding universe, possibly playing a role in shaping its large-scale structure. Cosmic strings could have had a significant impact on the early universe, particularly in influencing the distribution of matter and the formation of galaxies. The gravitational pull of cosmic strings could have acted as a sort of scaffolding, guiding the collapse of matter into the structures we observe today. Some theories suggest that cosmic strings could have contributed to the formation of galaxy clusters, or even superclusters, which are the largest structures in the universe. Interestingly, cosmic strings might also help explain certain anomalies in the cosmic microwave background, CMB radiation. The CMB is the faint glow of radiation left over from the Big Bang, and it provides a snapshot of the universe when it was just 380,000 years old. Although the CMB is remarkably uniform, there are small fluctuations in its temperature that correspond to regions of slightly higher or lower density. These fluctuations are thought to be the seeds of the galaxies and other structures that formed later in the universe's history. Some scientists have proposed that cosmic strings could have left subtle imprints on the CMB, potentially explaining some of the observed anomalies in its temperature distribution. Detecting these imprints could provide indirect evidence for the existence of cosmic strings. The search for cosmic strings has been ongoing for decades, and while we have yet to find definitive proof, scientists continue to explore several avenues for detection. One promising method involves looking for the gravitational lensing effects of cosmic strings on distant galaxies. By scanning large portions of the sky and looking for the distinctive lensing patterns that cosmic strings would produce, astronomers hope to catch a glimpse of these elusive objects. Another approach involves searching for gravitational waves produced by cosmic strings. As gravitational wave observatories become more sensitive, they may be able to detect the faint ripples in space-time caused by cosmic string interactions. There are also efforts to detect the effects of cosmic strings on the cosmic microwave background. Although the primary fluctuations in the CMB are thought to be caused by quantum fluctuations in the early universe, cosmic strings could leave secondary imprints that might be detectable with high-precision measurements. Scientists are looking for specific patterns in the polarization and temperature distribution of the CMB that could be indicative of cosmic strings. The Alcubierre drive. The dream of faster-than-light (FTL) travel has long fascinated scientists, science fiction writers, and anyone who has looked up at the stars and wondered what it would be like to explore distant galaxies. The main obstacle to this dream is a fundamental rule in physics. Nothing can travel faster than the speed of light. This limit, established by Einstein's theory of relativity, has been a hard wall in the pursuit of interstellar travel. However, a theoretical concept known as the Alcubierre drive offers a tantalizing possibility. What if, instead of trying to move an object through space faster than light, we could warp space itself around the object? The Alcubierre drive, named after physicist Miguel Alcubierre, proposes doing just that, allowing a spacecraft to travel to distant stars faster than light, without violating the laws of physics. The idea of the Alcubierre drive stems from the theory of general relativity, which describes how massive objects warp the fabric of space-time around them. Gravity, as Einstein showed, isn't just a force pulling objects together, but rather the result of space-time curving around massive objects like planets and stars. In principle, if space itself can be bent and warped, then maybe it could also be manipulated in such a way as to allow faster-than-light travel. The Alcubierre drive operates by creating what's known as a warp bubble. The idea is to compress space-time in front of the spacecraft while expanding it behind the spacecraft. Within this bubble, the spacecraft would essentially be riding a wave of space-time, much like a surfer rides a wave on the ocean. Crucially, the spacecraft itself wouldn't be moving faster than the speed of light within the bubble. Instead, it's the space around it that would be moving. This avoids breaking the speed limit imposed by special relativity, since the spacecraft isn't technically traveling faster than light, it's space-time itself that's doing the moving. This concept of warping space, rather than moving through it, offers a clever workaround to the problem of FTL travel. By manipulating the structure of space-time, the Alcubierre drive sidesteps the issues of relativistic travel, such as time dilation, where objects moving close to the speed of light experience time at a slower rate. In the Alcubierre drive scenario, the spacecraft and its occupants remain in a sort of bubble of normal space, free from the effects of relativistic travel, even as they traverse vast distances in what would appear to outside observers as faster-than-light motion. While this concept sounds promising, the practical challenges of building an Alcubierre drive are immense. One of the major hurdles is the need for exotic matter to create the warp bubble. Exotic matter is a form of matter that has negative energy density, something not known to exist naturally in our universe. While quantum physics predicts the existence of certain effects, like the Casimir effect, that involve negative energy in small amounts, the kind of large-scale negative energy required to create a stable warp bubble has never been observed. In Alcubierre's original paper, he estimated that the amount of exotic matter needed for a warp drive would be roughly equivalent to the mass energy of the entire observable universe. More recent studies have suggested that this requirement could be reduced to the mass energy of a small planet, but even this would still be far beyond our current technological capabilities. The sheer amount of energy required to manipulate space-time on such a scale presents a significant barrier to the development of a working Alcubierre drive. Another challenge is the stability of the warp bubble itself. Even if we could create the negative energy necessary to form the bubble, there's no guarantee that it would remain stable or that it could be controlled in a way that would allow for safe travel. Theoretical models suggest that the bubble could collapse or behave unpredictably, posing a risk to both the spacecraft and the surrounding environment. Additionally, some models predict that a warp drive could accumulate dangerous levels of radiation as it travels, which could be released in a catastrophic burst when the spacecraft exits the warp bubble. Despite these challenges, the theoretical framework of the Alcubierre drive remains an intriguing area of research for physicists. It touches on some of the deepest questions in modern physics, particularly regarding the nature of spacetime, energy, and the fundamental limits of travel. The concept also opens up interesting discussions about the potential consequences of FTL travel, particularly when it comes to causality and the nature of time. One of the most profound implications of FTL travel is its potential to violate causality. Causality is the principle that cause precedes effect. In other words, an event cannot happen before its cause. This seems like a basic rule of the universe, but FTL travel could disrupt this order. If a spacecraft were able to travel faster than light, it could, in theory, arrive at a destination before it left. This would lead to all kinds of paradoxes, such as the possibility of an event happening before its cause, which could break our understanding of time. These time paradoxes are a major problem for any theory of FTL travel. In some scenarios, FTL travel could allow for closed time-like curves, which are paths through spacetime that loop back on themselves, effectively allowing for time travel. For example, a spacecraft could travel to a distant star faster than light, then turn around and arrive back at Earth before it left. This creates logical paradoxes, such as the possibility of changing past events or causing contradictions in the timeline. These violations of causality are a major reason why many physicists are skeptical of FTL travel, even in a theoretical context. The laws of physics, as we understand them, are built on the assumption that cause and effect follow a linear progression through time. If FTL travel were possible, it could undermine this foundation, leading to a universe where time itself becomes unstable or unpredictable. The Alcubierre drive, while theoretically consistent with general relativity, still raises questions about how FTL travel would interact with the nature of time and causality. In recent years, there has been some renewed interest in warp drive concepts, partly spurred by advances in our understanding of quantum field theory and the development of new mathematical models that could reduce the energy requirements for an Alcubierre-style drive. While these models are still speculative, they suggest that FTL travel might not require the impossible levels of energy originally predicted, but could instead be achieved with more manageable amounts of exotic matter or other forms of negative energy. If a working warp drive were ever developed, the implications for humanity would be profound. It would open up the possibility of exploring distant galaxies and star systems in a matter of days or weeks, rather than the thousands or millions of years it would take with current propulsion technologies. Interstellar travel, long the domain of science fiction, could become a reality, allowing us to visit planets orbiting distant stars, search for extraterrestrial life, or even colonize other worlds. But the implications wouldn't stop with space exploration. Faster-than-light travel could also revolutionize our understanding of physics, leading to new insights into the nature of space-time, energy, and the universe itself. It could help us solve some of the biggest mysteries in modern physics, such as the nature of dark matter and dark energy, or the unification of quantum mechanics and general relativity. The development of a working warp drive would be one of the greatest achievements in human history, fundamentally changing our place in the universe and our understanding of reality. The fragile balance of universal stability. Now, in quantum field theory, the vacuum isn't the empty void we typically imagine. Instead, it's a state of the lowest possible energy for quantum fields that permeate the universe. But what if the universe isn't in its true lowest energy state? This is the concept of a false vacuum, where the universe exists in a metastable state. It may appear stable, but there's a lower energy state it could transition to. Essentially, the universe is sitting in a shallow valley of energy, stable for now, but with the potential to shift to a deeper, more stable valley, the true vacuum. This shift could occur through a process called quantum tunneling, with unpredictable and catastrophic results. Quantum tunneling is a phenomenon in quantum mechanics where particles can pass through barriers that they wouldn't be able to overcome in classical physics. When applied to the entire universe, it suggests that the universe could tunnel from a false vacuum state to a true vacuum state without needing any external trigger. This transition is random and could happen at any time, or it might never happen at all. But if it did, the consequences would be dramatic. The energy difference between the false and true vacuum states would be released in an enormous burst, creating a bubble of true vacuum that would expand outward at the speed of light. This expanding bubble would destroy everything in its path. Inside the bubble, the laws of physics would be radically different. Particles that once had mass might lose it. Fundamental forces like electromagnetism could behave differently, and the very structure of space-time could change. Matter, as we know it, wouldn't be able to survive in this new vacuum state. Stars, planets, and even atoms would be annihilated. The bubble would expand relentlessly, consuming everything in the universe without warning. Because the bubble travels at the speed of light, we wouldn't see it coming. It would simply arrive, and all matter and structure would be obliterated. While the idea of the universe spontaneously transitioning to a true vacuum is unsettling, it remains purely theoretical. There is no direct evidence that we are in a false vacuum, but it's a possibility raised by the principles of quantum mechanics. If the universe is in a false vacuum, the timing of such a transition is completely uncertain. It could happen billions of years from now, or it could happen tomorrow. However, the current age of the universe suggests that if vacuum decay is possible, it hasn't happened yet, and the universe appears stable for the time being. The discovery of the Higgs boson in 2012 has prompted new discussions about vacuum stability. The Higgs boson is linked to the Higgs field, which plays a critical role in giving particles mass. Its discovery was a major milestone in particle physics, but it also raised questions about the stability of the universe's vacuum state. Based on the current understanding of the Higgs field, some physicists believe the universe might indeed be in a metastable vacuum, where the Higgs field is in a local minimum rather than the true lowest energy state. To determine whether we are in a false vacuum or not, physicists study the properties of the Higgs boson and the mass of other particles, like the top quark. The mass of the Higgs boson is a critical factor in understanding whether the universe is stable or on the edge of instability. So far, calculations suggest that the universe is metastable, meaning it's stable for now, but there's a possibility of vacuum decay in the distant future. This metastability implies that the universe is safe for at least billions of years, but it leaves open the unsettling question of what might happen on cosmic timescales. Quantum tunneling is a slow process on large scales, and the energy required to trigger a vacuum decay event could be incredibly high. This means that although the universe might be metastable, the chances of a vacuum decay event occurring in our lifetime, or even over the next billion years, are exceedingly small. However, it's also impossible to predict exactly when such an event might happen, if it's possible at all. The fact that the universe has existed for over 13 billion years without undergoing such a transition suggests that if false vacuum decay can happen, it likely requires conditions far beyond anything we currently observe. Ongoing research is attempting to determine whether the universe is truly metastable and whether there might be signs of vacuum decay. High-energy particle experiments, such as those conducted at the Large Hadron Collider, LHC, offer insight into the conditions of the early universe and the behavior of quantum fields, like the Higgs field. By smashing particles together at incredibly high energies, physicists hope to better understand the properties of the Higgs field and other fields that influence the stability of the vacuum. Some theoretical models predict that high-energy events, such as those recreated in particle accelerators, could give us clues about the vacuum state of the universe. These collisions might not directly cause vacuum decay, but they could reveal more about the underlying structure of the vacuum and whether the universe is in a stable or metastable state. Additionally, cosmological observations of the universe's large-scale structure and the cosmic microwave background, CMB radiation, might also offer indirect evidence about the vacuum's stability. False vacuum decay would be an extremely rare event, and detecting signs of vacuum instability would be difficult. However, by examining the early universe's evolution and how quantum fields behaved during the Big Bang, scientists might find evidence of past phase transitions that could provide clues about the universe's vacuum state. The CMB, for example, offers a snapshot of the universe just 380,000 years after the Big Bang and could hold information about the behavior of quantum fields during that time. Another potential way to detect signs of vacuum instability is by searching for gravitational waves. Gravitational waves, ripples in space-time caused by massive cosmic events, could potentially carry signatures of past vacuum transitions. While no such gravitational waves have been detected so far, upcoming detectors like the Laser Interferometer Space Antenna, LISA, could help in the search. If vacuum decay or similar phenomena occurred early in the universe's history, their effects could be imprinted on the cosmic background radiation or the fabric of space-time itself. Despite the speculative nature of false vacuum decay, the study of vacuum stability raises profound questions about the ultimate fate of the universe. If the universe is indeed metastable, there's a possibility that it could transition to a true vacuum at some point in the distant future. The consequences of such a transition would be far-reaching, reshaping the fundamental laws of physics and obliterating the universe as we know it. However, the vast timescales involved make it unlikely that we'll ever experience such an event. Time loops in the warp of space. One fascinating concept in theoretical physics is the idea of closed time-like curves, CTCs, which are solutions to Einstein's equations of general relativity. They represent paths in space-time that loop back on themselves, creating the potential for time travel. In a closed time-like curve, an object or person could follow a trajectory through space and time that eventually leads them back to their starting point, not just in space, but in time as well. This means that events in the future could influence the past, leading to potential violations of causality, where the effect of an event could precede its cause. The idea of CTCs raises profound questions about the nature of time, causality, and the limits of our current understanding of the universe. In Einstein's theory of general relativity, gravity is understood as the curvature of spacetime caused by the presence of mass and energy. Massive objects like stars and planets curve spacetime around them, and this curvature affects how objects move through both space and time. While most of the solutions to Einstein's equations describe everyday scenarios like planets orbiting stars or the expansion of the universe, there are more exotic solutions that allow for the possibility of closed time-like curves. These CTCs are paths through space-time where an object traveling along the curve would eventually return to an earlier point in time, creating the possibility of a time loop. One of the earliest and most famous examples of a space-time solution that allows for closed time-like curves is known as Gödel's universe. In 1949, the mathematician and physicist Kurt Gödel discovered a solution to Einstein's field equations that described a rotating universe. In this rotating universe, the structure of spacetime would be twisted in such a way that an object could travel along a closed loop in time, returning to its starting point in both space and time. Gödel's solution was an intriguing example of how general relativity might allow for time travel, even though the universe we live in does not appear to resemble Gödel's rotating universe. While Gödel's universe is a theoretical construct that doesn't match our own, the possibility of closed time-like curves isn't limited to this specific solution. CTCs can also arise in other theoretical models, particularly those involving highly curved or distorted regions of spacetime. In these scenarios, spacetime could be twisted or bent in such a way that time loops become possible, allowing for the existence of CTCs. The existence of closed time-like curves raises significant concerns about causality, the fundamental principle that cause precedes effect. In our everyday experience, causality seems to be a basic rule of the universe. If you drop a glass, it shatters, and the shattering is the result of the glass being dropped. But in a universe with closed, time-like curves, this order could be reversed. An event in the future could influence an event in the past, leading to paradoxes and potential violations of causality. One famous example of such a paradox is the grandfather paradox, where a person travels back in time and prevents their own grandfather from meeting their grandmother. If this were to happen, the time traveler would never be born, which raises the question of how they could have traveled back in time in the first place. These kinds of paradoxes illustrate the challenges posed by CTCs to our understanding of time and causality. The potential for causality violations makes CTCs highly controversial in theoretical physics. Some physicists argue that nature must have a way to prevent these kinds of paradoxes from occurring, while others believe that CTCs are simply not possible in the real world. However, the equations of general relativity don't explicitly forbid the existence of CTCs, which leaves open the possibility that they could exist under certain extreme conditions. Wormholes, which are hypothetical tunnels through spacetime, offer another potential way for closed time-like curves to form. A traversable wormhole could, in theory, connect two different points in spacetime, allowing for instantaneous travel between distant locations. If one end of the wormhole were moved at near light speeds, or placed in a strong gravitational field, time dilation could cause time to pass more slowly at one end of the wormhole than the other. In this case, a person entering the wormhole could emerge at the other end at an earlier time, effectively creating a closed, time-like curve and enabling time travel. The idea that wormholes could create CTCs is intriguing, but it also raises the same concerns about causality violations and time paradoxes. Moreover, the existence of traversable wormholes is purely hypothetical at this point. While general relativity allows for the possibility of wormholes, creating and stabilizing them would require exotic forms of matter with negative energy density, which have yet to be observed in nature. Without such exotic matter, wormholes are likely to collapse too quickly for anything to pass through them, making them impractical for time travel. Despite the challenges posed by CTCs, some physicists have speculated that quantum mechanics might offer a way to resolve the paradoxes associated with time loops. Quantum mechanics, which governs the behavior of particles at the smallest scales, introduces the concept of quantum uncertainty, where the outcomes of events are not deterministic, but instead governed by probabilities. Some researchers have suggested that quantum mechanics might enforce consistency in closed time-like curves by ensuring that any event that occurs in a time loop must be self-consistent, meaning that paradoxical situations like the grandfather paradox would be avoided. In this view, quantum mechanics could impose constraints on what can happen in a closed time-like curve. For example, if a person were to travel back in time, they could only do so in a way that ensures they don't create a paradox. The events in the time loop would self-correct, leading to a consistent history where the cause and effect relationships are preserved, even within the context of a CTC. This idea is sometimes referred to as the Novikov self-consistency principle, which states that any action taken by a time traveler must be consistent with the history they experienced. Quantum mechanics also introduces the possibility of multiple timelines or parallel universes, which could offer another way to resolve the paradoxes associated with CTCs. In this scenario, traveling back in time could create a new alternate timeline, separate from the original one. This would allow for the possibility of time travel without causing paradoxes, as events in the new timeline would not affect the original timeline. While this idea is speculative and not widely accepted, it represents one possible way to reconcile closed, time-like curves with the principles of causality. Quantum tunneling. Quantum tunneling is a striking example of how the rules of quantum mechanics diverge from our classical understanding of the world. In classical physics, if an object doesn't have enough energy to overcome a barrier, it's stuck. There's no chance it will cross that barrier. But at the quantum level, particles aren't confined by such rigid rules. Instead, they exist in a state of probability, and in certain situations, they can tunnel through barriers that classical physics would deem impenetrable. This phenomenon, quantum tunneling, defies our everyday experiences, yet it's crucial in numerous processes, both in nature and in technological applications. It's this escape from classical boundaries that fuels some of the most essential reactions in the universe, and it hints at far-reaching implications for our understanding of the cosmos. At its core, quantum tunneling occurs because particles aren't merely particles in the quantum world. They also behave as waves. According to the wave-like nature of particles, described by quantum mechanics, the location of a particle is not fixed until it's measured. Instead, it has a probability distribution that spreads out over space. This probability wave can extend into regions where, classically, the particle would have no right to be. Even if the particle lacks the energy to overcome a physical barrier, part of its probability wave can extend through the barrier, meaning there's a small but non-zero chance that the particle will appear on the other side. This is the essence of quantum tunneling. One of the most important places quantum tunneling takes place is within stars, including our Sun. Stars produce energy through nuclear fusion, a process where lighter atomic nuclei, like hydrogen, combine to form heavier nuclei, like helium, releasing vast amounts of energy in the process. The fusion of nuclei is essential for stars to shine, but there's a significant obstacle. Nuclei are all positively charged, and as such, they repel each other due to the electromagnetic force. The closer two nuclei get, the stronger this repulsive force becomes, making it seem impossible for fusion to occur at the temperatures and pressures present inside stars, at least according to classical physics. However, quantum tunneling provides the solution. Even though the nuclei inside stars don't have enough energy to overcome the electromagnetic repulsion in a classical sense, quantum mechanics allows them to tunnel through the barrier. This means that protons, the positively charged nuclei of hydrogen, can get close enough for the strong nuclear force, the force that binds protons and neutrons together in atomic nuclei, to take over, allowing fusion to occur. Without quantum tunneling, the Sun and other stars wouldn't be able to produce the energy that powers them, and life as we know it wouldn't exist. Tunneling is also crucial in superconductivity, a phenomenon that occurs in certain materials at very low temperatures, where they conduct electricity without resistance. In typical materials, electrons face resistance as they move, colliding with atoms in the material and losing energy in the form of heat. But in superconductors, electrons form what are called Cooper pairs, pairs of electrons that move together through the material without scattering. This zero-resistance movement is what makes superconductors so remarkable. Quantum tunneling comes into play when two superconductors are placed next to each other, with a thin insulating layer between them. Even though, classically, electrons shouldn't be able to cross this insulating barrier, quantum tunneling allows Cooper pairs to tunnel through the barrier, maintaining the superconducting current. This tunneling phenomenon is the basis for the Josephson effect, which is critical for applications such as superconducting quantum interference devices, SQUIDs, used in sensitive magnetic field detectors and in certain types of quantum computers. Another key example of quantum tunneling in nature is alpha decay, a form of radioactive decay. In alpha decay, an atomic nucleus emits an alpha particle, which consists of 2 protons and 2 neutrons. Classically, the alpha particle is trapped inside the nucleus by the strong nuclear force, and it doesn't have enough energy to overcome this force and escape. But through quantum tunneling, the alpha particle can escape the nucleus, even though it doesn't have enough energy to overcome the nuclear barrier directly. This process occurs spontaneously in certain radioactive elements, and it's one of the reasons that elements like uranium and radium decay over time, releasing radiation. Beyond its role in stars, superconductors, and radioactive decay, quantum tunneling also plays a part in speculative ideas about the very fabric of the universe. One such idea comes from inflationary cosmology, the theory that the universe underwent an incredibly rapid expansion in its earliest moments, just fractions of a second after the Big Bang. This period of rapid expansion, called inflation, helped explain why the universe is so uniform on large scales. However, inflation may not have ended uniformly across all regions of space, leading to a scenario known as eternal inflation. In eternal inflation, different regions of space experience inflation at different rates, leading to the formation of pocket universes. Each of these pocket universes could have different physical properties, depending on the conditions in the region where inflation slowed and stopped. Quantum tunneling plays a role in this process, as regions of space could tunnel from one vacuum state, a higher energy state, to another, a lower energy state, creating bubbles of space where inflation stops and a new universe begins. This tunneling between vacuum states is a key part of the multiverse hypothesis, the idea that our universe is just one of many universes, each with its own unique physical laws and constants. In this framework, quantum tunneling could be the mechanism by which new universes are born. As regions of space tunnel to lower energy states, they form new independent universes, each with its own vacuum state. Some of these universes might resemble ours, while others could have entirely different laws of physics. Quantum fluctuations play a critical role in this process as well. During inflation, small quantum fluctuations in the energy of space could cause different regions to inflate at different rates, leading to the creation of new pockets of space that could evolve into separate universes. These fluctuations, which occur at the tiniest scales, are blown up to cosmic sizes during inflation, and their imprints can still be seen today in the cosmic microwave background radiation, the afterglow of the Big Bang. These imprints are the seeds of the large-scale structure of the universe, influencing how galaxies, stars, and clusters of galaxies form over billions of years. Eternal inflation, coupled with quantum tunneling, leads to a picture of the universe that is constantly expanding and creating new regions, each with its own unique properties. This concept ties into string theory's landscape, which posits that there are many possible vacuum states, each corresponding to a different set of physical laws. In this picture, our universe is just one point in this vast landscape, and quantum tunneling allows regions of space to move between different points in the landscape, creating new universes in the process. While quantum tunneling plays a speculative role in the creation of new universes, it's also a well-established phenomenon in both everyday and extreme processes, from powering the sun to enabling superconductivity and explaining radioactive decay. It highlights the bizarre yet incredibly powerful nature of quantum mechanics, a field where particles can seemingly defy classical logic, passing through barriers and reshaping our understanding of reality. I hope you enjoyed this video. If you did, feel free to leave a like and subscribe to the channel. Thanks for watching.